So today it's going to be me and Brian and Tyler, which will join us a bit later, hosting the recitation. So first, three announcements. Owner is out of town right now, so today his office hour is canceled. If you have questions, he'll be back tomorrow. You can send him an email if you have like urgent problems. And second, a reminder, the project proposal due September 30th. I think that's next Monday. So make sure you started thinking about your project and then starting writing about your proposal. And if you don't know yet, the project ideas are listed on the course website. So make sure you have look at that. Today the agenda is basically I will cover some basics about simulators. If you haven't had any experience before, it will be a good thing to look at. And then mainly it will be a discussion about potential projects. Like if you have any questions, it will be a good place to ask right now. Like we can discuss. So for simulators, there are really two kinds of simulators. One is called trace-driven simulation. The other is called event-driven simulation. The trace-driven simulation is pretty simple. It basically pre-records the instruction stream from execution of a program. Usually is done by some binary instrumentation tools, such as Intel Pin tool. And then the instruction stream is later fed to a timing model. Basically, you put timing stamps, like this load takes 400 cycles, that store takes 600 cycles, and then you simulate the behavior. How much cycles will they affect? There are pros and cons using this kind of simulation. The pros are it's basically very simple because you don't need to worry about how the instructions are fetched, how they are executed. You just need to get them from the execution. And then you basically just need to write a timing model. And then it's very fast because it's just a math model. It's basically counting how many cycles this instruction will incur. So when you run it, it's probably pretty fast. It's easier to debug as well. The cons is mainly you cannot react to dynamic events such as like branch misprediction because what you get is basically a fixed stream. You cannot say go back in time. Now this is I force it to mispredict, and now I want to correct it. It won't happen that way. So it's pretty fixed execution. You can't change the execution direction. Basically, you can't change the control flow. I'll give an example about that later. So execution-driven is, on the other hand, it's basically a program which fetch and execute the instructions on the fly. So you can understand that way. That is, the next instruction will not get executed before the first instruction finishes. So it's really simulating the CPU. It fetches instruction, execute it, fetch the next one, execute the next one. If there's a misprediction of the branch, it will go into the wrong way until it gets corrected. So it's a CPU in a software. So there are several examples. For example, like M5 or the GM5, which is M5 plus a very accurate memory model as well. And then multi-tool sim, which has CPU and GPU in a single simulator. You can simulate their interactions as well. So let me give you a higher overview of execution-driven simulation. So usually there's an infinite loop that contains different execution stages. For example, like typically in multi-tool sim or Gen5, you'll see there's an infinite loop that's called those different functions. Each function is basically a stage, like fetch, dispatch, issue, execute, write back, retire memory. And internally, it has data structures simulating, for example, ROB and RS, which are reorder buffer and reservation stations, and also register files, which basically interacts with those function calls. And then usually, they also have a function called process events, sort of like that. It processes architectural events, for example, a branch misprediction, an interrupt, such like that. So this is a high overview. Usually, execution-driven simulator has two components. One is called the front end. One is called the back end. So the front end usually just take care of reading, extracting instructions from a binary code file. It reads binaries and fetches instructions from a program. It predicts branches. It updates program counter to the next instruction, so on and so forth. The backend simulates the internal structures of a CPU. It putting instructions into the ROB, decode them, and then issue them when they're ready, and also write back, update the register files. The front end and back end, they're interactive. So for example, if the back ends discover there's a misprediction from the front end, later on during the execution stage, it will update the correct PC and tell the front end, hey, you're on the wrong track, and probably you should correct it, flush the pipeline, etc. So they're interactive. The benefit of having execution-driven is it's very accurate. It's cycle accurate because for trace-driven simulation, you don't really capture those like how deep did I go into the wrong mispredicted path, how many cycles does it take. You are basically just simulating high-level cross-grain like events, like for example a cache miss. But for execution-driven simulation, you can simulate very, very accurately with like tiny architectural events. For example, like branch misprediction. That's a good example. And also, yeah. So basically, that's you can also handle dynamic events such as like context switches or branch misprediction. The big drawbacks are, first of all, it's very complex because you are simulating an entire CPU. It's not like trace-driven. You are just providing a timing model, provide a mathematical model. Here, you have to take care of extracting instructions, handling events, handling those ROBs, RS, handling those corner cases where there's a stall or there's a ROB fall, like handling mispredictions, stuff like that. So it's pretty complex. And then it's much, much slower when you're running it because for each instruction, you basically take it out and you have to do lots of extra work of it, putting into ROB, into RS, issue it to a function unit. Until then, you can get it executed. And still you have to take care of like writing it back. So when you run them, it's probably like 100x or even more, 1,000x or even more slowdown of running a program on a single computer. So that's the main drawback. And it's harder to debug as well. Here I will provide two case studies of using trace-driven simulation and execution simulation. So the first case is, for example, we want to measure the performance gain of a new memory scheduling we want to measure the performance gain of a new memory scheduling policy, not performance. Sorry about that. So for this case, we can use trace-driven simulation because cache miss and memory scheduling policy in memory controller is a cross event when you do like compared to cache misses. Compared to branch predictions. So usually we'll use Intel Pin, which is a binary instrumentation tool to get all the loads and stores from the execution stream of a program. And then we'll get those instructions with their address and data as well. Then we just feed the stream into a timing model where, for example, we say each load will take like 500 cycles, each store takes 600 cycles, and then there's probably a turnaround penalty. Like if you, between load and store, there will probably be a turnaround penalty. And then you can simulate like if we batch all the loads together and we batch all the stores together, rather than we just let first come first serve policy, how much benefit can we gain? So that's one example. And then here's a case study of execution-driven or event-driven simulation. So the case is we want to measure the performance gain of using run-ahead. Probably owner have already talked about that in speculation. So run-ahead is basically instead of when you have a cache miss, and then you're going to the memory, which is very slow. Instead of letting the processor stall right there, you can speculatively run ahead, keep running, and then capture all the future cache misses on the fly. So in the future, when your cache miss comes back, when you continue to run, you won't get stalled again in the future load. In the future load. But for that, we need to set the processor keep running after a cache miss, which means an event-driven simulation can't do that. So basically, trace-driven simulation cannot do that. So for in this case, we use execution-driven simulation, which basically we set the front end of the execution simulator to instead of stalling on a cache miss, we can speculate. We can we can ask the backend to set a checkpoint, and then continue to fetch instructions. And once the data comes back, your cache miss comes back, the backend signals the front end saying, "Oh, I have the data back," and then the front end will reload the PC, the program counter of the checkpoint, and then flush the entire pipeline. So this is another case of using execution-driven simulation. Yeah.
So why can't we use trace-driven here?
So trace-driven is.
Please repeat.
Oh, sorry. Okay. So the question was, why in this case you cannot use trace-driven simulation? So trace-driven is basically you run it once, from beginning to end. The program finishes.
You have the sequence of instructions, right?
You have.
And then you're just executing and then speculating.
So
You can still do that.
So trace-driven usually just captures some traces. So it doesn't know about program counter. You just say add store, for example, add, divide, jump, add, jump, store, for example. You don't know what this jump is jumping to. It's just an execution. You cannot say.
You can actually capture that data in a trace.
So
Like you don't have to use it.
I see what's your point.
Can you repeat the point that she's making?
Um,
The data could just detect your dependencies, which is already really neat in Planet.
so the second question is, if you have all the execution anyways, why can't you just simulate you are running ahead? Yep. So I think ideally you would, but then during your when you are running ahead, if there is a branch, right, you probably won't be able to predict that branch precisely. For example, if that branch is depending on your data, then you have to branch to a different path. While when you do trace-driven, then what can happen is when the data comes back, when it's keep executing, it will probably have an accurate branch prediction. It will go to the correct path. But when you're doing running ahead, you probably go to the mispredict path, right? With trace-driven, you cannot simulate, you can only simulate assuming it will go to the correct path.
Wrong path activity.
Yeah, so you cannot really force it to go to the wrong path. Yeah. So in a sense, it's less accurate, but it's faster. You can always assume if I run ahead, I will always run ahead as if the data has come back, right? In that sense, trace-driven and execution-driven won't differ that much. But without that assumption, I mean, yeah, basically they're different.
And are you using the words event-driven and execution-driven in between? I thought there was
No, event-driven. So the question was, why I'm using event-driven and execution-driven interchangeably. So I apologize for this. This should really be execution-driven. Usually, event-driven are interchangeably with trace-driven, because trace can also be event. For example, a cache miss can be an event, or it can be a trace of like instructions. So you can either be a trace of events or a trace of instructions. So that's a mistake by me. Let me.
So,
yeah.
Owner's raised his hand. I guess if he'd like to speak. Owner, would you like to say something?
Do you have your cable sound key?
Oh.
I'm muting my power microphone.
Okay.
If you'd like to speak.
This isn't microphone enabled. Just give it a second.
Hello?
Yes.
Are you able to hear me? Oh, okay. I thought anyone over there.
You guys able to hear him? A little bit? Not really.
Okay. Okay, I guess I'll speak. It's kind of odd not to receive any feedback, but as long as you said I'm out of time, but I've been following the discussion and I need to go for meetings soon. I don't know if you can see me. I can enable the video as well. So let's test this while we're away, I guess.
Yep, go for
Would
it.
to enable my video?
How do I enable his video?
Enable it.
Let's
Enable
see.
it. So,
Got my webcam. Okay. You're able to see me now.
not yet.
Okay, it feels like I'm speaking to myself, but I just want to make a couple of comments based on the discussion. I think Hongi presented a view of trace-driven versus execution, and that's at the very two extremes. It really, in simulation, you can have a trace, and you can try to emulate what execution looks like. The major difference between trace-driven and execution-driven is, in trace-driven, you collect a dynamic stream of events beforehand. And if the execution actually changes that dynamic stream, and if you don't have those events in the dynamic stream, you cannot basically model it. That's the major difference. For example, you get a set of instructions as part of your instruction trace, and in random execution, for example, you may need to execute some different trace based on the load miss stream. For example, if your trace doesn't contain the instructions that you need to execute to model run-ahead execution, then you will lose accuracy. So I think that's the key distinction between trace-driven and execution-driven. Trace-driven, you've already collected a trace, a dynamic stream of events, and when you're simulating, I guess what's happening, or what would happen in a different architecture, if that dynamic stream of events doesn't contain what you're actually trying to model, or what the new architecture that you're testing leads to in terms of the execution events, then you won't be accurate in that case. Now people have tried to make different ways of making trace-driven more accurate. For example, you can try to reconstruct some of the events. Let's say you don't have the trace of run path instructions. You can try to find some instructions. You can actually try to reconstruct the binary itself just by looking at the trace, right, if you have enough information on the trace. So any questions on this?
Don't have any questions?
No questions. Okay. Let me actually just make a couple of announcements. I'll need to leave in 10 minutes or so, and then I'll leave it to Hongi. Is my screen being shared now?
No,
No, you can if you would like to.
I can.
Projector's gonna take
Oh, okay.
To click start sharing, I think.
Let's see, start sharing. I'll need to get used to this.
Yeah, the little camera icon at the top.
Oh, there you go. Okay, share my screen. Let's try to do this. Desktop. I'll just give you a couple of references, I think, related to trace-driven execution-driven. Just if you're interested in this. And, okay, that's not what I want. One is, there was a paper that we had done in 2006 on looking at the effects of wrong path memory references. So, for example, if you have a trace-driven execution that doesn't model the wrong path really well, you can help performance in that case. And this may matter in out-of-order and run-ahead execution processors. I'd recommend this paper that's over here, an analysis of the performance impact of wrong path memory references on out-of-order and run-ahead execution processors to see one difference between trace-driven and execution-driven simulation. And now you could argue that actually you can make the trace-driven simulation more accurate to be able to model wrong path references, but if you read the paper, it can briefly talk about that also. The other I would recommend is this one. It's a short paper. It's published in Computer Architecture Letters. It gives a quick overview of simulation in computer architecture, and it's basically it's a 4-page paper. You can take a look at it. It tells you a general overview of what a simulator looks like. For example, this is actually an execution-driven simulation over here, but you can actually use traces over here as well. So you have functional model and the timing model distinction that we talked about in an earlier recitation session. But I wanted to provide you with this reference, this up online after the recitation session. I guess finally, my last announcement is unrelated to simulation. It's about the calcium seminars. Since all of you are interested in computer architecture, I would encourage you to attend the computer architecture seminars that we have at Carnegie Mellon. And this is the website for that. Search for calcium computer architecture lab at Carnegie Mellon. It's not the calcium element. This it could be if you look at this picture over here. But we have seminars coming up, and some of them have already happened. One was actually on simulation. You can probably look up the paper related to that. But there will be a seminar coming up on October 8th, October 15th, October 22nd, and October 28th and November 1st. I guess November 5th also. So if you would like to get announcements related to that, you can subscribe to this mailing list by clicking this link or emailing Dave Weiss, who's organizing the semester seminars.
It's usually in Hammerschlag.
Let me get back to Adobe. Yes.
I'm saying it's usually in Hammerschlag D level.
That's right. They're usually at Hammerschlag D level, but they can change also. So if you actually, let me see. If you actually become part of that mailing list, you will announcements. And I encourage everyone who's taking the class to become part of this calcium mailing list, because you get other events related to computer architecture on that list. Okay, so one of the questions Mihir is asking online is, are these recorded as well? They're actually not recorded, but we could try recording them. That's a good question. I think, let me take a look into that. Any questions for me before I leave? Okay, I guess I don't hear anything, but I will see you all during the recitation session on Friday. And I'll leave it to Hongi and my other TAs now.
Sounds good.
Yeah.
Thank you, owner.
Thank you.
Owner, you have a nice room.
Okay, thanks. Thanks, bye-bye.
All right. So exit full screen.
Okay. Yeah, so for that paper, I will just cover a little bit extension, as owner said. So the paper was about so sometimes when you do a misprediction, right, you probably will do useless work because you will flush a pipeline eventually. But sometimes it's actually not that useless. For example, usually on the wrong path, even though the execution will be different, but sometimes you still encounter the same load of the same data, right? Like you read if and else, right? You probably say if this, then do this execution. But then the data you need is probably the same. So even if you go to the wrong path, you still issue some loads that you will issue anyways, right? So some of the cache miss you can capture seems to be actually useful. And for those, you need to simulate wrong paths really, really well. And then if you cannot do an accurate simulation, that's what the owner mentioned, then your result won't be as accurate, right? Because you just say, we're going to ignore all the wrong paths, then you won't even encounter those prefetches, right, from the wrong path. So that's something I want to elaborate a little bit more on. I guess that's pretty much my talk about simulations. So the rest of the recitation is basically we can openly discuss your potential projects. What's your questions? And Brian and I can answer some of the questions. Sure.
How long do the project proposals need to be?
So
Can you repeat the question?
so the question is how well or how long the proposal need to be.
Thank you.
I would say 1 to 2 pages.
Yeah, page or two.
Yeah, it doesn't need to be very long.
It's more important to be like concrete in like what you want to do and be detailed enough that we can like easily set milestones. Well, you set milestones for yourself what you should be doing, but it doesn't have to be super lengthy.
Yeah, so Brian's answer is doesn't need to be super lengthy, but it's preferred to be very concrete. You can set your own goals, what you want to do at October sometime, what you want to achieve at November sometime, and you eventually. So it's actually good if you can set, for example, 3 goals. Like the acceptable goal is what, the perfect goal is what, like, and then this like the owner used to call it moonshot goal. It's like something impossible to do in one. But what if you achieve that? Who knows? So it's good to set 3 goals, and then accordingly set your milestone goals. It doesn't need to be very short, very lengthy, but please mention what's the problem you want to solve, what's the current solution, briefly discuss about literary search you did, and then, what's your goal? So that's your proposal.
So
Yeah.
it's up to us when our milestones are defined by us. It's just like internal tracking for our own.
Yes. So we'll probably have 2 milestone meetings. So the question is, the proposal is basically, the milestone is for the students who keep track of themselves. So the milestone will probably have 1 or 2 milestone meetings. We'll help you like decide, have you met your milestone goals? And if you haven't, how can we improve on that? What should we do? So that's what's milestone purpose. Yeah.
How interested are you guys in real-time scheduling and like just schedulability analysis of tasks, which is slightly sort of up the stack from hardcore hardware?
Sorry, can you elaborate a little bit more on that question?
How interested would you be in such a project? Or would you say this belongs in some other class, like operating systems class? Or do you think this is an acceptable topic to look at the schedulability of real-time tasks?
I think this is an acceptable project. Like, measuring performance. Well, so the question is, what do we think about projects such as managing, scheduling tasks on a real-time system? Will that be some topic that will that be some topics that is acceptable for this class? I think that's acceptable. Measuring performance by scheduling, different scheduling on a real architecture, on a real processor, and then monitoring what's the basic properties that can affect the performance. For example, running on an Atom in-order core might be drastically different from running on a Xeon server core, where they have different one is in order, one is out of order, one has little cache, one has lots of cache. Memory channel, also there's a difference. So if you can parse out all the different factors and how they change your program, and ideally propose, for example, in the future architecture for this application, we prefer to have, for example, out of order or in order, how many channels, high bandwidth or low bandwidth, what's the bottleneck right now? That will be an acceptable project, I think.
Any other discussion questions? Yeah, I should remind also that all the TAs and professor will have office hours, so the proposal is due on Monday. I would suggest if you're shaky at all, feel free to type up a draft and send it to the list or come meet with us in person, and we'll try to fix it up for you.
Yeah, so Brian was saying we all have office hours, professors and TAs. So if you have questions about your draft or maybe just want to have the TA to look at it, feel free to send emails to TAs and professors. Yeah.
What if two groups are interested in the same project idea?
So what if two groups are interested in the same project in the end? I don't think I have the authority to give you a precise answer. You might want to ask this question to the professor again. But I think it's acceptable. It doesn't really matter if two groups can carry out some results. That will be something telling me maybe this result is more reliable, for example. So for me, it seems like it's acceptable. But you want to further discuss, do the two groups interact each other, collaborate in any means? So that depends.
As long as you don't go directly along the same path.
Yeah. Yeah. If no further questions, then this pretty much is it. If you have any questions, feel free to send emails to any TAs. We'll be happy to answer your questions. To discuss research topics, just schedule an appointment. And also owners, students, including me and other PhD students at the fourth floor of CIC, they are all open to discuss. Many of them in the group works on DRAM, scheduling policies, and personally I'm working on DNA sequencing acceleration. So if you're interested in any of the projects, feel free to ask to talk to any TAs, NT and any students.
Can you send me the slides that you used today so I can upload them up to the Yale?
Yeah. Should I send to? Yeah. So those slides will be uploaded onto Akatar, and then also the course website.
Will you provide a simulator or will you provide a
Will I what? Sorry.
Will you provide a simulator? Let's say
Oh, the simulator. So yeah, I was probably, yeah. Sorry, I forgot about that. Okay. So.
Can you share your screen again?
Okay, so here are some simulators, just typical simulators. In the group, we had people similar with Multi-Tool Sim. That's one of the recent simulators we have been using. And Pin generally is a good tool to extract traces. That's also a tool like lots of people have experience. There are other tools. One of the most famous, I guess, is Gen 5. Lots of people in the field use this simulator. But the first three up here. Also, like some of the PhD students in the group, they also have their own simulators. For example, Yinggu Kim is one of the fifth-year PhD student of Honor, and he uses his own simulator to simulate DRAM response, like scheduling policy and response. It's very detailed DRAM simulation. So if you want to do any DRAM simulation research, you're welcome to ask Yinggu.
So Mihir asks, are the simulators available using VPN?
VPN, like .NET.
VPN.
I think they're just free simulators on the web. You can download it, and then if you want to use any in-house simulators, just send an email to the students, ask for them. They'll probably give you a branch of the JIT. Yeah. Yeah, I'm pretty sure Multi-Tool Sim Pin, they're all downloadable from web for free. So, and Gen 5. GPU Sim is another simulator for GPUs. If you want to do any simulation on GPU, I suggest GPU Sim rather than Multi-Tool Sim, although Multi-Tool Sim can also simulate GPUs. But GPU is more standard, GPU Sim. If you want to do any simulation cooperating CPU and GPU, then you should probably use Multi-Tool Sim. Brian, do you have anything to add on? No. Yeah, so pretty much it. Good luck on proposals, and feel free to send an email to us. If any of you want to talk to me afterwards, you can. I'll be staying here until 1:30. Yeah. Okay. Thanks.